Welcome to my channel Chemistry Not Mystery. You can also visit my website chemistrynotmystery.com. Today's topic is Bohr's atomic model. Watch this video till the end to learn all about Bohr's atomic model and to understand what are the postulates of Bohr's model. What is an orbit? How much is the energy of Bohr's orbit? What is Bohr's radius? What is the Bohr's frequency rule? Explanation of hydrogen spectrum by Bohr and the limitations of Bohr's atomic model. Bohr's atomic model was specifically for the hydrogen atom. Niels Bohr proposed the structure of hydrogen atom and also gave quantitative explanation of the hydrogen spectrum. To explain his model, he gave some postulates. So let's see what these postulates are. Electron in the hydrogen atom can move around the nucleus in a circular path of fixed radius and energy. These paths are called orbits or stationary states or allowed energy levels. These orbits are arranged concentrically around the nucleus. They are numbered as 1, 2, 3, 4 and so on. These integral numbers are known as principal quantum numbers. The next postulate is energy of an electron in orbit does not change with time. Electron will move from lower stationary state to higher stationary state when it absorbs required amount of energy. An electron emits energy when it will move to the lower stationary state from the higher stationary state. Energy change does not take place in a continuous manner. It is absorbed and released in small bundles of energy, that is quantum, as we studied in Planck's quantum theory. Bohr also explained the way to calculate the frequency of absorbed or emitted radiations during transition of electron from one stationary state to another. It is given by the formula delta E upon H, or you can say E2 minus E1 divided by H, where E1 is the energy of lower stationary state or orbit and E2 is the energy of higher stationary state and H is the Planck's constant. It is also known as Bohr's frequency rule. Bohr also calculated the angular momentum of an electron in a given stationary state as mvr is equal to n h upon 2 pi, where n is equal to 1, 2, 3 and so on. And me is the mass of electron, v is the velocity of electron, r is the radius of that orbit, and h is the Planck's constant. Bohr said that electron can move only in those orbits for which its angular momentum is integral multiple of h upon 2 pi. That's why only certain orbits are allowed. Bohr also gave the formula to calculate the radius of an orbit, where r is equal to n square multiplied by a naught, where n is the principal quantum number or the number of orbit, a naught is a constant and its value is 52.9 picometer or 52.9 into 10 raised to minus 12 meter. Here, r is directly proportional to the n square. That means the radius of orbit increases with increase in the principal quantum number. Bohr also gave the formula to calculate the energy of an orbit. En is equal to minus Rh multiplied by 1 upon n square, where n is the principal quantum number or the number of orbit, Rh is the Rydberg's constant and its value is 2.18 into 10 raised to minus 18 joule. If you have watched my video on hydrogen spectrum, you might get confused here with the value of Rydberg constant. In hydrogen spectrum, the value of Rydberg constant is 109678 cm inverse. And this difference in the value is because of the change in the unit. One more thing we must have noticed here, that there is a negative sign in front of the energy. Let's see, why is the energy of Bohr's orbit negative? Negative sign signifies that the energy of an electron present in the atom is less than that of free electron. Because electron present in that atom is bound with the force of attraction of the nucleus, while free electron is free from any attractive forces. The free electron is considered to be present at the infinity orbit of atom. When you put the value of principal quantum number equal to infinity, you will find that the energy of infinite orbit is equal to 0 joule. That's why energy of any orbit n is always less than that of infinite orbit, that is 0. That's why it is always negative. How does the energy of Bohr's orbit varies with the number of orbit? Let's calculate. The energy of first orbit of hydrogen comes out to be minus 2.18 into 10 raised to minus 18 joule. And the energy of second orbit of hydrogen comes out to be minus 0.545 into 10 raised to minus 18 joule. You must be familiar with the number scale. Values present on the left side of 0 are negative. Negative values, that is closer to the 0, is greater. That means on increasing the value of principal quantum number, energy of orbit increases. Here, the energy of second orbit is more than that of first orbit. Or on moving away from the nucleus, energy of orbit increases. Bohr actually gave his model only for hydrogen atom, so that it can be applicable only to the ions containing one electron. Here is the generalized formula for energy. En is equal to minus Rh in bracket Z square upon N square bracket close, where Z is the atomic number. Here E is directly proportional to the Z square, so that the energy of orbit becomes more negative for the element has higher atomic number. And this formula can be applicable to the ions like helium plus, lithium 2 plus, beryllium 3 plus, boron 4 plus, and so on. Bohr's model is a primitive model of atom, but it explains the line spectrum of hydrogen and also explains the reason for the structure of Rydberg's formula. If you haven't watched my video of hydrogen spectrum, you can find its link in the description box. According to the Bohr's postulates, radiation or energy is absorbed if the electron is moved from orbit of smaller quantum number to the orbit of higher quantum number. The amount of energy released is equal to the difference in energies of the corresponding orbitals. Now the question is, how much energy is absorbed or released during the transition? Bohr also calculated it by subtracting the value of energy of final and initial state. So delta E is equal to energy of final orbit minus energy of initial orbit. So delta E is equal to minus RH upon N final square minus RH N initial square. Now take out the RH common. Delta E is equal to RH in bracket minus 1 upon NH square plus 1 upon Ni square. So here negative value comes first. So we can rearrange the equation and we get delta E is equal to RH in bracket 1 upon N initial square minus 1 upon N final square bracket close. By using this formula, we come to know that how much energy difference is there, but when energy is absorbed and when it will be released. Let's see. In the case when N initial is less than N final, then the fraction 1 upon N initial will be greater than 1 upon N final. so the delta E will be positive. This positive side indicates that electron will absorb energy during transition. Now see in which condition energy will be released. Radiation or energy is released if the electron is moved from orbit of higher principal quantum number to the orbit of smaller principal quantum number. The amount of energy released is equal to the difference in energies of corresponding orbitals. So how much energy is released? In the case when n initial is greater than the n final, then the fraction of 1 upon n initial will be lesser than the 1 upon n final. In that case, delta E will become negative, and here the negative sign indicates that the electron will release energy during the transition. We have seen in the hydrogen spectrum there are a number of lines, while in hydrogen atom there is only one electron. So why does this show a number of different lines of different frequencies? Bohr gave the reason for it. If there are a large number of hydrogen atoms, there would be a large number of possible transitions that leads to the large number of spectral lines. And the intensity of spectral lines depends on the number of photons. Now come to the limitations of Bohr's model. It fails to explain the finer details of hydrogen spectrum, like closely spaced lines called doublets. These closely spaced lines can be observed by sophisticated spectroscopic techniques. Another limitation of Bohr's atomic model is it was unable to explain the splitting of lines in magnetic field, that is Zeeman effect. It was also unable to explain the splitting of lines in electric field, that is Stark effect. The another limitation of Bohr's model is that it could not explain the ability of atoms to form chemical bonds. I hope you understand now the Bohr's atomic model of hydrogen. But even if you have any doubt, you can post in the comment box. And don't forget to like and share this video. And to get more such videos, please subscribe to the channel and press the bell icon to get notifications. You can also join my Telegram channel. Thanks for watching. Keep learning. Stay safe.